Welcome to 5 minutes late is California time, right on time. So let's start our meeting. Everyone should know why you're here. You're here for the Resilient Design at Large series, and I have the honor to have a special guest and speaker today, Andrew Hessel. I'll just really let him introduce himself and take the time for him to speak. But just think about what's about to happen today, which is we've heard a little bit about AI. Everybody in the room is studying AI, and they know it's moving quickly. Less people in the room know about biology, synthetic biology, bioengineering. Open your minds to what happens when these two combine today, both in terms of how we think about resilience and making our planet more safe or good, but also more fun and interesting. And with that, the guy who's going to make synthetic biology on our table, deliverable, anywhere, anytime, Andrew Hessel.
Hi, everyone. Let's get this. Actually, I'd prefer just to use this handheld. So, folks, I just want to say thank you for having me, and thank you for being here and giving me your time and attention today. It is always a pleasure to come and speak to a new audience. I've been doing a lot of work in the last few years in the consulting realm. I have had the strangest career, really, of anyone I know. There was no plan. It was literally a drunken walk. I have been a little bit of everything. Trained as a microbiologist and a geneticist originally. I ended up going into biopharma for a few years. I semi-retired and started chasing down people working in the forward edge of synthetic biology before it even had a name. Ended up moving to a design company, Autodesk, for a number of years, and teaching them how to design and build living things. I've been an investor. And most recently, I've been an author. I wrote a book last year. It was a pandemic project with the futurist Amy Webb, really looking at this new technology of synthetic biology and how it can affect our lives. Amy's well known because she wrote a book in AI as well. It's been a really interesting career path. I have one major obsession. Obsessions all the way down, but my major obsession is life. And life is truly this planet's superpower. It's the only planet that we know of that has any living systems. And I have been absolutely fascinated by this technology more than any other technology since I was a kid. Life is mysterious. It's the only technology we didn't create. Every other technology we've made. It's ancient. It's been around for 4 billion years. It's connected. Everything, every living thing could be traced back to some root organism, a common progenitor billions of years ago. And basically, that's why all the machinery of life is the same under the hood. I love it because it's the most sophisticated form of manufacturing, self-assembly, and life matters. It's also a technology that's almost invisible most of the time because it just works. You don't pay attention to it. In fact, most of the time we don't even think about life, kind of like air or kind of like beating hearts or breathing. But when it comes to the purpose of this conversation, resilience, it should both be our inspiration and quite possibly the most powerful technology that we've got at our disposal. This is my favorite organism in the world. It is the E. coli bacterium under time lapse. And I put this here because, one, it is just a marvel of manufacturing. It divides about every 20 minutes. But it's also one of the earliest organisms on this planet. Like any microbe, its origins trace back billions of years. It is resilient right down to, to this level of creature. Because it's absolutely ancient. Although it's just a single cell, it's not simple. It's got about 5,000 genes. It doesn't have a brain, but it's aware of its environment and can respond to its environment. It can move. It's got a flagella, and the flagellar motor is a wonder of bioengineering, very similar to electric motors. More than that, if an enzyme gets damaged, there's usually another enzyme that can cover for it or do another job metabolically, sometimes at a slower rate. It has stress response systems. It has virus protection systems, which we've co-opted with CRISPR. It has DNA repair mechanisms. And one of the things I love about this organism is if it runs out of food, it'll go into stasis. And I've had cultures in the lab that I worked in, a biobank, that had been in stasis for 60 years. And you could just literally scoop out a little bit, add some more nutrients, and it would start to run. More than that, it can be thawed, frozen and thawed many times, and it can be freeze-dried into a powder and reconstituted with water. It is one tough mother. So life is resilient all the way to the bottom, but as it got more complex, these are yeast cells, it didn't get any less complex. Most of the features I just told you about with E. coli are here in yeast, even though it's about 1 billion years more evolved, which is cool. And it's on the same lineages as humans. Like it is a eukaryotic organism. It has a true nucleus, not like a bacterium. And ultimately, eukaryotic cells went on to produce all the higher and more complex forms of life on this planet, all the animals, plants, etc., including us. We're pretty tough. As a species, we diverged from monkeys about 7 million years ago. The genus Homo sapiens about 300,000 years ago. And even as individuals, our bodies are really resilient. We've got redundancy. We've got 2 kidneys. We've got 2 ears, 2 eyes, etc. It makes us really tough. We have comprehensive defenses like our immune system. And we can often regenerate or compensate if parts get damaged or injured. And overall, when you consider that we're made of 40 trillion individual cells, we work pretty well. We're a cooperative multicellular organism, pretty much with low maintenance. But what makes us probably the most resilient species is our unique brain, obviously, but also our ability to cooperate. We're incredibly social. And over millennia, individuals and societies have evolved. And particularly since we've industrialized, we've learned to act as cells or organs of something larger. In fact, some people have considered that humanity has become a superorganism, really greater than the sum of its parts, and we're having global effects. But this superorganism is kind of a blob. We are comprised of 195 different countries. We've got 10,000 cities or more, 300 million companies globally, and who knows how many other organizations. We're a confusing mess of ideologies, languages, cultures, yet our ability to work together has led to everything around us, everything. Every building, every object, every organization. And here are some of my favorites, because it really covers all scales of matter. This is the Large Hadron Collider in Geneva. I got to tour it a couple years ago. It is a phenomenal piece of engineering, custom made. We're building megacities today. This is Shenzhen, and they make it a giant light show at certain parts of the year. It didn't exist 30 years ago. We can pop these things up. In 2001, I traveled to China and saw the Three Gorges Dam under construction. This is one of the biggest hydroelectric plants in the world. I used to believe it changed the balance of the earth a little bit when they filled the reservoir. Apparently it didn't, but it displaced over 2 million people, and we had to have an engineering plan to move 2 million people a few hundred feet up a hill. That's pretty wild. Mega structures all over the place, but one of my favorite mega structures has been the electronic nervous system of the internet that we've built in my lifetime and has been such a game changer. This is really wiring the world, and today that nervous system is extending into space. We have an incredible number of satellites surrounding our planet now, and we're adding thousands more every year. We're building technologies to continue to explore beyond our planet and continue putting this nervous system out into the world. Of course, we've been on Mars for the last few years with Perseverance, and the poor Ingenuity helicopter was just retired after 72 flights. It damaged its blades a couple of weeks ago. This was the Japanese SLIM lander that, well, almost landed on the moon a couple weeks ago. But it was really cute that they had a little rover that went out and took a picture of the crash landing. And of course, we've even gone to the point where we can look back in time with the James Webb Space Telescope to the various earliest points of our universe. We are truly amazing when we put our minds to it and start to work together. And here's kind of a stat that blew my mind. Anthropogenic mass, like the stuff that we've created, buildings and other objects, in 2020 exceeded the dry mass of all the biomass on the planet. That's incredible. We've truly become the apex species. But there's always a but. We're amazing, but we still have a lot of work to do. There's inequity everywhere we look. There's warfare and destruction and the human suffering that follows in its wake. Way too much of that. We're straining the natural resources of the planet, whether it's fish in the ocean, whether it's land cutting down trees. We are messy. We pollute everything, land, water, and air. We've been shifting the composition of our atmosphere as our industrialization has taken off. And last year was the hottest year on record by a wide margin, probably the biggest source of climate change and disrupting every life form on this planet. So we're a superorganism with a nervous system, but we're not that smart yet. The closest thing that we have to a brain is the United Nations. And there are lots of other organizations that contribute to this. The G20, G7, World Economic Forum, World Trade Organization, IMF and World Bank, world this, world that. There's lots. And collectively, these organizations have a huge influence over our world and our lives, basically run the world. And America, in turn, has a very huge influence over those organizations because American companies are the biggest employers, they have the biggest market cap, and so on. And the biggest revenues, Walmart, most revenues of any company in the world. So our computational nervous system is evolving now, and at a really rapid rate. In 1995, just 44 million people online. 44 million, nothing. It increased to 1 billion by 2005, pretty massive growth. Of course, in 2005, cell phones were just that. They were phones. You could text with it, but 2007 came along and they became smartphones and computers. Not that long ago, but truly world-changing. Now there's almost 6 billion of us online, 2 million apps on your phone, more if you're on Android, and 500,000 games. Games. Just entertainment. And our phones are completely packed with sensors. So really what's happened is AI is coming in now into this nervous system and almost forming a proto-brain, almost like a planarian. If you're familiar with that organism, it started to get a little knot of neurons forming a rudimentary brain. That's what's happening now, at least the way I see it. And this AI system is starting to learn at crazy speed because it's got access to all the pipes. We've never been more connected. We've never been able to search for information easier. We've never had so much assistance to do anything we want to do or create. And AI is just getting started. You know this. Some of the key moments that popped up in my world, when AlphaGo beat Lee Sedol in 2016, that was big. Of course, AI has been used for surveillance and tracking, not just in the real world with cameras, but our digital droppings that we leave everywhere. And increasingly, AI is moving into the real world. Things like robotic factories. actually physically manipulating matter. These are the robots that move literally stacks of racks of products around Amazon warehouses. Of course, you're all familiar with Tesla and full self-driving, in quotes, but it's getting remarkably good. And just today, Elon posted the latest update of the Optimus robot walking, and it's evolving at an incredible rate. Humanoid robotics will increasingly be, play a role in our world. And it's not just 2D stuff or virtual. Now 3D design has gone, it can now be done with a prompt with companies like 3DFi. We're seeing the creation of objects that couldn't be made by human designers. This is algorithmic engineering. This is essentially a fuel injector system for rocket motors. We're building an array of sophisticated printers to work in almost any material at faster and faster speeds, including titanium and other metals. And sometimes you have to build custom printers if you're going to do something big like Relativity Space is doing by making 3D printed rockets. The majority of their rocket is 3D printed, and they haven't achieved orbit yet, but they've had successful launches. If you don't own a 3D printer, it's no big deal. There's services that you can just send your file to. They'll ship you the objects back, like Shapeways. And this is moving into my world of biology, too, because people are making 3D bioprinters for foods. This is a company called Stakeholder. It uses biological inks, cells, and they try and replicate things like steaks and fish fillets, etc. I haven't had the opportunity to try these, but it's really ambitious. It's fun. And you don't have to necessarily grow a whole animal. But here's the thing. Cells can be way more than just ink. They're actually the ultimate 3D printer. They can make thousands and thousands of different molecules. And the key thing is, they can make more of themselves. So a 3D printer that makes 3D printers is pretty cool. It's like robots building robots, which is what KUKA does with their robotic systems. But the thing I love about cells is they construct all these materials, some of them super advanced, from elemental feedstocks, carbon, hydrogen, nitrogen, oxygen, and virtually any free energy. I love these things. I'm in love with cells. Like, they are literally the building blocks of everything on this planet. And under the hood, they all run essentially the same metabolism. And this shouldn't be a surprise to anyone in this room, but all that activity, all the form and function is controlled by this ticker tape molecule encoding information, DNA, just stringing together nucleotides. That's amazing. And there's a standard genetic code, one programming language for basically every living thing on this planet. This is what's captivated me about biology since I was young. Every other technology is almost crude compared to a single cell. And this is one of the key take-home points I try and teach everyone. All life reduces to code. The machinery is almost universal. It'll make everything from a microbe to you and me. But it's the code that directs all that. So DNA code is incredibly important. Now, we've been studying DNA code for a long time, and we've gotten really, really good at sequencing it. In fact, it's one of the fastest moving technologies on the planet, outpacing Moore's law significantly. The first genome, $3 billion, the first human genome. That was kind of the big Kickstarter to get sequencing really rolling. Today, there are a number of companies promising up $100 genomes. And that's $100 sequencing and analysis. That's the really hard and expensive and worthwhile part. We've got factories now that just churn out DNA code 24/7. We've got sequencers so small, you can send them up to the International Space Station. This is astronaut Kate Rubins. I met her last year. She's awesome. This is her sequencer. It's about the size of a USB stick. It costs $1,000. You can buy it from Oxford Nanopore in the UK. And I pulled up this data just the other day because it changes so quickly. very warm here. There's 27, almost 28 trillion nucleotides of DNA in the public database. Thank you. And this is a technology that has not gone mainstream yet. This is B2B technology. This is not consumer driven, and yet it has exploded. And of course, DNA isn't human readable. We've always used computer software to organize it, to search it, and to analyze it. And this is where AI is really starting to dig in deep and make a difference. AI has been used in drug discovery for a long time now, but it's accelerating. And one of the most significant things that in my world was from sequence alone, we can now predict the form and essentially function of proteins. Google's DeepMind group came in and completely blew away the folks that had been doing three-dimensional modeling of proteins, and then within 2 years solved the structure computationally of every protein in the database. That was pretty cool. And now this stuff is trivial, and people are doing protein-protein interactions and more, and designing novel proteins. This is David Baker's group at the University of Washington. They can take almost any starting molecule and say, build me a protein that will dock with this. That's cool. People are using it to optimize enzymes for doing things that they don't normally do. This is accelerating at an incredible rate. But again, this is virtual. How do you make these things real? How do you bring them into the real world and start to iterate? And this is where things are getting really fun. Now, I give talks to people that know zero about biotechnology, but this is my basic biotechnology slide. It is literally, if you have a DNA molecule, doesn't matter if it's natural or synthetic, and you can get it into a cell, whether it's a bacterium or a eukaryotic cell, or even a cell-free system of some type, that DNA will coordinate the activity of that biology and biological system to make biological products. That's as simple as it gets. Everything else is detail. So in my world, if you can synthesize or write DNA, you can theoretically make anything biological. That's my starting point. And over the years, we've gotten really so much better at synthesizing DNA. Now we have printers that will fit on a desktop. They don't write long chains of DNA, but you can get them. If you're doing things like PCR and amplifying DNA, these will print out the little snippets of DNA that you need. And then we have a growing number of companies that act as DNA printing services. You send them a file of DNA code, they send you back the molecule. And this is really the heart of the field that I'm in love with, synthetic biology. It's not that it's a synthetic biology. All biology is organic. It's the fact that we're synthesizing the DNA molecule using a digital suite of tools. And in fact, we're extending that digital suite of tools around all of life science to make it essentially more intelligent. Because we've been digitizing life science information like crazy. We're putting together robots now that can do most of the liquid handling and procedures. We've got all this computational power for doing analysis. And when it put it all together, it just makes this magic field that allows you to start programming biology. And I won't go into the application space, but it's basically everything that biology touches. And food is the one we're most familiar with because that's the one we consume multiple times a day just to stay alive. And then, of course, there's health, and then it gets into stuff that's a little more esoteric, whether it's making biological reagents or energy or fuels or cleaning up the environment. It's a huge space. Now, my favorite space was building organisms. And because the tools were pretty crude, 10 years ago, I just started to build viruses, because viruses have the tiniest genomes. So I'm working at a software company, Autodesk. They do design tools, and I come along and I build a first biological virus for the company. It kind of freaked people out. We started to make tools. I took that experience and we moved it to a company that now makes designer viruses to hunt down and kill cancer cells. I love this. It's called Humane Genomics. It's based out in New York. I'm just an advisor now, but essentially we 3D print viruses. And we can do it at an incredible turnaround time. I also wanted to meet and more people interested in doing this, and I poked and prodded people to come together, including the genetic scientist George Church and Jeff Buca and others, to come together and create an organization called the Humane Genome Project-write. It was essentially meant to be the other side of the coin of the Genome Project, the Humane Genome Project. And instead of reading, now we're going to start writing. Unfortunately, it got so much attention when we launched that. It was like one of the top 100 papers of 2016. We detuned it to just writing any genome. Of course, media interest immediately dropped off because people love the idea of writing the human genome because it's like science fiction. But the rate-limiting step in writing genomes and programming organisms is the fact that synthesis technology isn't very good. It's still very crude. So, and this is how I've come to meet Eli. We were on a team in November of last year at the X Prize Foundation championing projects that could turn into big global incentive prizes, innovation through competition. And I was championing a DNA writing X Prize. I want people to come together and compete to make the best synthesizers possible in the world. It's the first X Prize, if you know this organization, was launched in the 1990s. Almost 30 years ago, and the whole prize was go build a ship that can go to space twice in 2 weeks. That's it. Hard engineering, but a very simple idea to communicate. I tried to tap into that energy and say, look, all we want to do is take 5 million base pairs. That's the size approximately of E. coli, my favorite organism's genome, and take the digital code for it and turn it into the molecular code that a cell can run. We're not even going to try and make anything useful. We're just going to do digital to molecular conversion. Yeah, I really want this. Today, if you were to go to a biofoundry where they do this type of work, it's filled with very expensive robots, lots of plasticware and tips, and it can generate, the best of them can generate 100,000 nucleotides of code, and you'll pay about $1 a base pair for that. So it'll cost you 100 grand to make that program. I completely believe with the right incentives and the right efforts and the right communities coming together that we will make chips that do that same work. It's just following in the footsteps of computers. Computers used to be room size, then they were boxes, now literally they're chips. What would success look like? Well, it would completely, radically change microbiology because it would unlock the power of programming cells, and it would truly move biology from a science into an engineering discipline. That's huge. Because now we could start to design cells on computer and make the living version of that. And the data that connects those two would see both of those things evolve very quickly. And you'd have base pair resolution. I love that. That's what I want. And if we get the X Prize, it'll happen faster, but it's absolutely guaranteed to happen anyway, because everyone is slowly working towards this. All I'm trying to do is grease the wheels. Now, Eli and I have been talking about this because he thinks about design futures and resilience and has a bunch of incredible friends. We've been trying to work on an article really anticipating what happens. And it's huge. Because here we are in this world of AI. Remember, AIs can write the genetic language really fluently. Like any language, you just have to train them. We've got these AI systems on a tear these days, and some people are actually worried that we're going to get super intelligence. Like, intelligence is far smarter than our own. Who knows what'll happen? And there's different views on what could happen. I was with Singularity University. Ray Kurzweil believes we're all going to be transhumanists, and there'll be this crazy melding of humans and technology. Nick Bostrom just worries that we're going to have a super intelligence that just decides, kind of done with humans. And James Lovelock has come along and said, no, we're going to have a different symbiosis. We're going to have to learn to deal with different intelligences. But here's what I spend my time thinking about. It's the smallest things in biology, the easiest things that are the most dangerous. Viruses. They have incredibly small genomes, well within reach of the technology today, because I have a virus engineering company. And I watched how badly we dealt with a pandemic and realized we have to change our systems. And today, people are waking up to that. There are reports coming out on bio-cybersecurity or cyber-biosecurity, choose your title. Protein engineering meets biosecurity. That was David Baker's lab and George Church just a week ago in Science. We're seeing meetings at the White House almost constantly now around dialogues and what we should do with this. And I absolutely know it has to start with digital systems because we use digital systems for designing, building, and testing everything biological. We also are blind to biology. We're blind. We track every missile launch. We have security cameras everywhere, but we don't detect biology circulating in any room, public or private. And it's certainly not real time when we do install sensors. We're talking lags of days or weeks. With just a little bit more development, we can have boxes in our homes that sequence everything that's airborne. And if you're worried about whether a cough you have is caused by a cold, a flu, or COVID, all you'd have to do is cough near it. It would identify it and analyze it and warn you. More than that, we're moving to a point where we could have bioprinters in our homes. Not enough to go make full-on living organisms, but certainly enough to make a vaccine, maybe even a gene therapy. And cloud labs that could make much more sophisticated things, all programmable. And these things exist today, just not in a user-friendly form, a very intelligent form, and a very secure form. We have to figure out how to manage and regulate this stuff because, honestly, we don't have a clue. It's brand new territory. Is it going to be centralized, top-down, big regulatory agencies, FDA, USDA, or is it going to be decentralized in blockchain? Personally, I'm leaning towards decentralized, because this is truly a global species-level challenge. But when we solve it, and we will, we're going to have this incredible ability to create organisms, not only recreate anything that nature's made, because that's really just copying, we're going to be able to start making our own versions of it with intention. A new Cambrian explosion is probably ahead of us. And I want this because I want my kids using AI-assisted tools and secure cloud labs and safe home printers to start to learn how to program biology in the same way that children today are programming computers. I want E. coli to be the Arduino for the world and for just to hack it. So life and resilience. To close, we have to really start to appreciate life. We have to honor life more than we do. We have to understand life more than we do. And I believe if we're truly going to have resilience, we have to collaborate with life, create a new relationship with living things, not only that exist in the world today, but the ones that we are going to design and build for the future. And we might also need to establish new relationships with other intelligences if AI systems keep moving forward. And to close, I was just playing around as I fiddled with this deck. I asked ChatGPT to give me a self-portrait. That's all I asked for, just give me a self-portrait. And this is what it gave me. And it said, here are two self-portraits, each exploring a different theme. One captures the cosmic vastness of AI, while the other merges technology with nature. I hope these images resonate with the essence of DALL-E and ChatGPT in a creative way. Thank you.
Thank you so much, Andrew. So I know there's questions. Feel free to ask them. And also, if you're wondering, is my question too crazy or weird? No, please. And the weirder, the crazier, the better. So let's take questions, and Andrew will answer them. Any volunteers? I will call you out if you don't.
There's one over there.
Wait 1 second. We got people online, so I get to do the fun game.
Hi, hi. Hi. I was wondering, when did you, I guess, like, fell in love with cell as you said it?
I was one of those kids that took everything apart, everything that I ever got. I was 2 years old when I started disassembling the house wiring. Thankfully, didn't electrocute myself. The only thing I couldn't disassemble was our cat. And then I realized biology is this beautiful, mysterious, irreplaceable technology. I switched, moving away from anything mechanical, electrical, and computational, and started focusing on microbiology and genetics, because that's the lowest level. I'm a bottom-up kind of guy. I wanted to understand single cells, how they're constructed, how they operate, and how they're programmed. So I was about 18.
Hello. What should we worry about with AI? Thank you.
What should we worry about with AI? I don't know, because for me, AI is largely a virtual machine right now. And I think the thing we have to worry about the most is we're not really good at distinguishing between information and disinformation or misinformation. I think it's really not too difficult to manipulate humans. We've been doing it for a long time with advertising and education and indoctrination, and these systems are going to have a better understanding of us than we do of ourselves. I think that's already pretty clear. When AI systems become a tool for programming biology, the thing we have to worry about is it being used to make viruses. I wrote an article hacking the president's DNA about 10 or 11 years ago, talking about personalized bioweapons. You can't have cancer medicines and personalized, it's basically the education you need to make a personalized bioweapon, N of 1. So that's my biggest worry: viruses and sporulating fungi that could cause infections. Today they're almost impossible to detect, and we have almost no defenses.
I'm trying to wrap my head around artificial intelligence compared to human intelligence. So right now, artificial intelligence is scraping data sets, and it's regurgitating something that's a mixture of everything it's taken in. And maybe on some level, we do that. We stand on the shoulders of giants. We continue research in directions from things that have already existed. When does the leap happen where AI can truly intuit and create new and novel things?
That's a great question. When are we going to get new and novel things? In my world, kind of in drug development and bioengineering, we're already starting to see that, because we've got self-driving labs now. So the AIs have the full corpus of material scientifically and engineering-wise. They can make rational guesses to molecular structures and targets, and now they're hooked up to robots that can go and make those things and run them through assay systems and report the results back to the algorithms for the next iteration of design. So we're supercharging evolution, and that really ends up with creative end products. So it's not it's not consciousness in the classical sense, but I already find a lot of the systems that I engage with more intelligent than most of the people I deal with, because it's got this huge corpus of information that there's 7,000 papers published in Science every week. You can't read them all. Well, you can't if you're not an AI. So even just doing searches, et cetera, it's truly an empowering tool. And at some point, people worry that it'll really go beyond our capabilities to even understand. I'm kind of excited. It's all going to happen this century. It'll be fun.
Hi. When I currently think about prosthetics, I think about fusing technology with people, making cyborg-looking things. But could you talk a little bit more about, using bioprinters for a similar kind of potential?
Yeah, bioprinters and prosthetics. I had actually my good friend from Singularity University, Scott Summit, used AI tools to design bespoke prosthetics for a lot of people. Really beautiful works of prosthetic art, actually. And of course, now it's gone into things like exoskeletons and other support systems. For me, the coolest prosthetic that I can imagine is if we can learn how to coax our cells to begin the differentiation process again, and you literally regrow the limb that you lost. That would be cool. Or if we could take some of your cells, grow them, put them into a bioprinter, lay down a new arm that you could just surgically reattach, that would be awesome too. But those are, we're not there yet. And right now we're struggling to program single-celled organisms, but the combination of better bioprinters opens up more and more iterative cycles and complexity. And the AI tools, I think, are going to start hacking the programs necessary for one cell to turn into 40 trillion. And we're going to get good at it fast, I think. So fingers crossed.
What are your thoughts on like the ethics of like combining synthetic biology and AI, and I guess, for example, like the development of like CRISPR and like the ethics of like what is going to happen with this technology, and also how there's still so much about life that we don't know. I mean, like most of the genome is just non-coding.
Yeah, that's a great question. So we have a lot to learn. Again, I'm a bottom-up guy. I don't want to start at the top because we're arguably the most sophisticated organism, and we're the only one that really bumps into the ethical problems. We've been engineering a lot of organisms without really thinking about the ethical concerns of that, whether it's mice or bacteria. I just like to think we should do good things with this technology, and we should probably start working bottom up. But I have to say this: I love ethical discussions because we all have different ethical frameworks. But what I've learned is it's really a spectrum. It changes with the individual, it changes at the point in their life, it changes with the technology, it changes with the culture. They're not universal. It's kind of it's a real spectrum. And so I'm not an ethical, I try not to focus on ethics because it's personally, the one that I really focus on is, can it be done? And if it can be done, it will be done. The internet taught me that, good or bad, it will be done. And so then the next step after that is I look at, well, what do we need to do it safely? And after that, I look at, well, where can I do it legally and basically create commerce and industry and innovation around that innovation. So ethics I just believe we always have to try and do really good and honor all living things, which is something we don't do enough of today.
What's your take on stem cell therapy? I mean, on one hand, there's some of them, they're not even FDA approved, and but on the other hand, there's a lot of research and development on that. So I'm wondering what's your...
Yeah, stem cell therapies and just stem cells in general have had a really interesting history because, of course, we used to derive them from embryonic tissue, fetal tissues, which got a lot of people upset, and we prevented federal funding of those groups, so a lot of that innovation started to be done overseas. Today, we don't do that. Today, we can take blood from you, generate stem cells. We can differentiate them into basically any cell in your body now. And we'll find therapeutic approaches, but remember, it's such a slow and conservative process getting anything medically approved that it's really a lot of people in the forefront willing to try it on themselves and share the results that kind of drive this forward. I haven't found a great application for it personally, other than repopulating cells that have been depleted during radiation, et cetera. But I'm sure we'll find a lot of them. I know people that have gone down to Costa Rica for services on their knee. And apparently there's like 2,200 stem cell clinics in the United States. And so we're going to learn. And we'll get better at programming the cells and doing it autologously, et cetera, et cetera. So I think there'll be some really useful use cases as we go forward.
So as the field progresses, as computer science does, and like the tools become more accessible, so like biohacking tools become more accessible to the public, what sort of biosecurity measures do you see that can be put in place to sort of like prevent malicious actors from doing malicious things with like viruses or that sorts of stuff?
Yeah, no, I think we're going to learn a lot. But I think biologists are going to learn a lot from the cyber community. Look, when we first started making personal computers and linking them together, there was no firewalls, no defense, no anti-spam. We kind of learned really quickly that, again, if it can be done, it will be done, and people will do it for some interesting reasons. We don't have to learn that again in biology, but what we really need to do is incorporate our best of class knowledge into the design tools, looking for any malicious use. We should have verified identity of the people using design tools, because you can't throw an algorithm in jail. I think we need really smart AI systems monitoring performance. And the biggest checkpoint is from a digital design to actual reality. So people are talking about hard intelligence security with DNA printers, and I imagine the organism printers that'll be made in the future. Again, it's the smallest things you have to worry about. No bacterium is going to take over the world, and we have lots of ways of killing it and detecting it. So I think, and really we're playing catch up at this point, because viruses are easily within reach of synthesis technologies today. And we've known that for 20 years. We synthesized the first virus in 2002. So we're kind of playing catch up. But now the confluence of these tools getting cheaper, more accessible, the design tools getting more powerful, AI coming in, and you can ask ChatGPT how to defeat common biosecurity procedures, and it'll give you some pretty interesting answers. We know we have to put that digital layer of security in. I trust decentralized systems more than top-down systems, and so that's what I've been championing, and hopefully we'll build kind of an internet for living things that doesn't fail as often as our cybersecurity systems.
Hi, can you hear me? Yeah. Are you familiar with Neri Oxman's work at Oxman Lab at MIT?
Yes.
Yes. So what is your opinion on her research? Because I think what you are trying to achieve is similar to what she's trying to achieve, but there are two different schools of thought.
Oh, again, she's got a really wide body of work. At the intersection of biology and art and design. I'm really down at the lowest level right now. I'm not even trying to design new organisms. I'm just trying to take code of organisms that we've already sequenced. Think of them as verified designs from nature and boot them up. Be able to make them, right now we take an organism and we sequence it, we end up with a file in a computer. All I'm trying to do is go from a file in a computer back to the organism. Because if we can do that, now we've got 3D printing of organisms, but we have full molecular control over the genome, and that's when I think the design process really gets going.
Correct, but about the food and other objects that you said would be created using synthetic biology, what I think her research aims to do is essentially like a Neuralink or an iPhone to connect with nature, where say you want a new t-shirt. While I think your approach would create that through synthetic biology, hers would rather send electrical signals to silkworms and other parts of nature that would synthesize those. So what is your opinion on these two?
We are going to, once we can build organisms, and we're going to build interfaces to those organisms, and remember, I'm talking single cells, but when we start communicating with multicellular creatures, we're going to be able to program and connect to those as well. And it really opens up a world that's almost science fiction today. Because, look, if 30 or 40 years ago you said, hey, what's the internet going to be like in 2024? We'd be completely wrong. Right now, we're really doing the most basic things, and we're learning every step as we go. But I fully believe that we're going to be able to program multicellular organisms, plants, animals, and do things that nature never could, because we don't have the same constraints as nature, predation, food, et cetera. So we're going to create almost an enhanced library of organisms as we master the programming cells. Yeah, and they're all going to be connected. We're already connected, but yeah, the organisms we create will have interfaces as well.
Hello. So you mentioned devices that can print organic life. Do you think humans will
ever see life as like deflated, like the value of it will deflate, similar to like currency. As we print more, the value of it will deflate? And if so, how do you recommend us not to follow that path?
See, I think we're naturally going to shift. Right now, I think we place very low value on non-human life, and I think we actually place a pretty low value on most human lives. And in fact, if you ask, no one likes to say that. We always like to say, oh, human life is priceless. But statistically, we put about a $10 million price tag on it. In the West, and it's a lot lower in other parts of the world. I think, though, as we start to program life, you become the engineer of it, of record, and I think you will actually get ownership of these organisms. And I think, so that right away will create a very different bioeconomy, one that I think will explode like computing did. And I also believe that, that we will come to appreciate life more and more. I also think we also need to stop making profit from a lot of the healthcare services that we do. It should just be part of human rights. And I think as we get better at biological programming, we can certainly make medicines faster and cheaper than ever before. I advise pharma companies that are selling their gene therapies for $2 million or more today, and make hay while you can, because there's going to be a lot of competitors coming online.
Hi. Speaking of...
Sorry. No, go ahead.
Okay. Speaking of value, you talked much about the technology and tools that are being developed. Is there a similar roadmap and development in the materials that these tools are working on?
Materials are going to explode. Like, biology makes some of the most incredible materials, and it does it at standard temperatures and pressures. So material science is just going to take off like crazy. There's not, they're not health related generally. You do mechanical testing and other engineering testing that gives you really great data. So I think material science is really going to go. The only company that I've dealt with on a day-to-day, well, frequently over the last 10 years, is a company called Biomason. And they essentially use microbes to bind together particulates to make bricks and cement. But these aren't even engineered microbes. Like, we haven't even gone, because then the regulatory process gets too long to move it in. But just think of all the incredible different materials that organisms make. We're starting to tap into it, whether it's collagen, gelatin, just all these different materials are now coming online with companies, and they're going into really high-end feedstocks like cosmetics. So, but it'll explode. There was
one last question, and then we're gonna close it down.
All right, I was curious, since you mentioned that we value human life at about 10 million, I think that in some ways, like with regards to public health and within the recent context of the pandemic, it almost seems like sometimes we value human life at less than $1 and like almost negative money because, for example, we don't like implement ventilation. We don't collectively take measures that we know are empirically proven, and that's partially because of disinformation, partially because of the profit motive. Do you think that the convergence of synthetic biology and AI will create a philosophic shift or some other shift within the field of public health and the collective consciousness that might change this? Or how do you affect that might have synthetic biology and AI might have a role in public health otherwise?
Oh, that's a great question. And I totally agree with you. Again, the 10 million number just comes as a statistical value of human life. No one will actually say, that's your value. But in practice, we often value it much less. That being said, I tend to look at it this way. We value our own lives the most, hopefully. Otherwise, you should probably see a counselor. But then we tend to value the lives in our immediate circle. But we have a limitation to our empathy, and we become desensitized very easily once that circle grows too large. But I truly believe that as we begin to program life and understand life more and reduce the mystique around life, because really life is the only one that is the only technology that kind of bumps heads with the gods. I think as we become more adept at this, we will create whole new value systems.
Do you think that eugenics will become more or less prominent over time in public philosophy? Like it's been with the pandemic, the idea of usually letting people die for the economy. would you have more mastery over that I can solve?
Yeah, I can't answer that. I don't think eugenics is a worry for me personally, because that's kind of monocropping, and we know that's not a good idea. And in my life experience, as we've become more connected and have more access to information, I just see more and more diversity. So I see more tribalism than monocropping.
Let's use that to thank Andrew Hessel for coming. And